Look at our first problem for this chapter. This one is again a thermodynamic process where we're going to only really look at 4 different things. So here we have air undergoes 3 processes in series. So we have an isothermal expansion. So we have isothermal expansion from point 1 to point 2, and that looks like a curve. We're not going to worry about the details of the curve and how it might look different than an adiabatic process. But isothermal does mean we have the work is equal to PV times the natural log of V2 over V1. Then a constant volume heating, so we go straight up. That one, the work is going to be easy. Work is equal to 0. And then constant pressure compression. So we're going this way, counterclockwise around this group. So it looks slightly different because the way the processes are ordered. So the constant pressure expansion work is going to be equal to P3, which will be the same as P1 times your change in volume. So part A is doing exactly that, asking us to figure out the work for each process. So for part A, we have an isothermal expansion. So work is equal to P1 V1 times the natural log of V2 over V1. We could also use P2 V2 times the natural log of V2 over V1, because we said that pressure times volume equals nRT. If we're constant temperature, all these things are constant. So we could also use nRT times the natural log of V2 over V1. So which one do we pick? Well, we got to pick the one that's the easiest. So we do have T1, P1, and V1, and V2, but we don't have P2, and we don't have the number of moles yet. So the easiest one to use is going to be this first one, because we have all the information. So P1 is 6 bar, and 6 bar is equal to basically 10 to the 5th pascals. So we're going to have to do that conversion. So 6 bar times 1 bar over 10 to the 5th pascals to get that right. And then our volume is 0.2 meters squared. And we're probably going to want to be in kilojoules. So I'm going to change, this is right now joules. So we're going to do kilojoules. We're going to divide by 100, sorry, 1,000 times the natural log of V2 over V1. V2 is 0.2 meters cubed, and V1 is 0.1 meters cubed. We got 6 bar times 10 to the 5th pascals per bar times 0.2. So this is our P. This is our volume. Then here we're just doing a kilojoules to joule conversion times the natural log. And for that one, we get 41.5 kilojoules as the amount of work done. Then we're going to look at the second part. So the work for this 1 to 2, process 2 to 3. We said work is equal to 0 because delta volume is equal to 0. And so process 3, 1. Then work, we said, is constant pressure process, so delta V. So this is going to be pressure 1 times the volume at 1 minus the volume at 3, because this is volume final, volume initial. Or we could use pressure at 3, but we don't know what the pressure is at 3 unless we use the logic that pressure at 3 is equal to pressure at 1 because it's a constant pressure process. So that's at 6 bar. So we'll do the same conversion as we did before. 6 bar times 10 to the 5th pascals per 1 bar. And then our change in volume. Now we're going the other way around. We're going from 0.2 to 0.1. So we end up at 0.1 minus 0.2. So we're going to end up with a negative work. And we're going to do the same unit conversion, kilojoules to kilojoules, because otherwise we end up with a really big number. And we get negative 60 kilojoules as the amount of work done for that process. And it should be no surprise that that is a bigger amount of work, because if we look at the PV diagram, we're looking at this big area underneath this curve, whereas this one is the relatively smaller area underneath that curve. It's all the same work, a little bit more nicely typed out, and you can see here a little bit better what I did. That here is all of our unit conversions from pascals to bar and from kilojoules to joules. Remember, Newton meter is a joule and a Newton per meter squared is the pascals, but I can still put these in so you can see more nicely how those things cancel out. I'm going to look at the mass contained in the cylinder, and for this we're going to use the ideal gas law. We're going to use the physicist version of it again. So like we did in class when we talked about the ideal gas law, the mass of air is, we're going to call the mass per mole divided by Avogadro's number. So the molecular weight of air is 29 grams per mole, and Avogadro's number is 6.022 times 10 to the 23rd molecules per mole, and that again gives us 4.816 times 10 to the negative 26 kilograms per molecule. So that's how much each molecule weighs. Now we're going to look at the ideal gas law. N is equal to PV over our Boltzmann constant times T. Again, this is like the number of things, not moles. So we have our 6 bar times 10 to the 5th newtons per meter squared per bar again. Get those to cancel out. And times our volume, 0.1 meters cubed. And then divide by our Boltzmann constant, 1.38 times 10 to the negative 23rd Newton meters per Kelvin, and 600 Kelvin, because that's what the temperature says we're starting out at. And so we get 7.41 times 10 to the 24th molecules. And then we put that in terms of our total mass, 7.41 times 10 to the 24th molecules times the weight of each molecule. That's the number we got before, 4.816 times 10 to the negative 26 kilograms per molecule. Gives us a total weight of just 0.356 kilograms. Here's all that nicely written out in case you didn't catch it on the last part. Now we want to look at the temperature and the pressure for state 2. So for the isothermal process, we know that P1 equals P2V2 over T2 is equal to NR. We also know that the temperatures are a constant, so P1V1 is equal to P2V2 is actually equal to nRT, because we know for the isothermal process the temperature remains constant. So now we can use just this part of the equation to find P2 is equal to P1V1 over V2. And so we don't even need to do the Pascal's conversion, 6 bar. And then we're going to look at the ratios of the volume, which basically means we need to divide by half. So P2 is equal to 3 bar. So now we can go up in here and label our graph, but that must be 3 bar. We know that the temperature 1 was 600 Kelvin, and so this also must be 600 Kelvin. So we're going to find the temperature for state 3. So for the constant volume process, we're going to use the same argument that we did before, except now it looks like P1 over T1 is equal to P2 over T2 is equal now to NR over V, because remember this is everything that remains constant. So we'll rearrange it again. T2 is equal to P2 over P1 times T1. So we got 3 bar over 6 bar in times 600K. So now we get 300K. So this point must be at 300K. And again, here's all that work a little bit more nicely written out. We have on the left the isothermal process and on the right the constant volume process. All using the ideal gas law because we hope this behaves as an ideal gas. Now we're going to look at the amount of heat transfer for process 2, 3. That is a constant volume process. So if it's a constant volume process, delta V is equal to 0. So that means work is equal to 0. That means if we look at our first law of thermodynamics, delta U is equal to Q plus W. If that's equal to 0, delta U is equal to Q, and Q is equal to MC delta T. And it's a constant volume process, so we need CV delta T. Given in the problem, up at the top is our heat capacity that we're going to use. So Q is equal to, we figured out the mass was 0.356 kilograms in part B, then 0.18 kilojoules per kilogram Kelvin. And then our temperature change we just figured out was 300 minus 600 K. So we get a net amount of heat transfer 76.68 kilojoules. This is that work nicely written out again. And we have a summary table looking at the amount of work done in each process. If this was thermodynamics class, we learned how to completely fill out this table and fill out the other Q's. We are not going to do that in this class. So they're all about the same order of magnitude in the 40s, 50s, 60s.